So we're going to do a quick aside before we continue on this to have a talk about the SIMD instructions and how we can use them. So the idea behind this, and I will put links to the lecture notes in the rest of the thing, is that we've got these set of headers here which give us a series of what we call intrinsics, which are instructions that the compiler will allow us to use, registers, special registers which are built into the thing. And in particular, the types that are there are data types that combine together rather than just a single float each time. We pack together, if we're using the SSE or AVX 1 to 8 types, 4 floats or 2 doubles or 16 bytes and so on like this. Or in particular, what we're going to use for this example is the AVX 256 types, which give us the ability to process 8 floats at once. Now, the advantage of this is that we can start to do some really interesting things. So far, if we were to, for example, add 2 floating point values together, in scalar mode, what's going to happen is we'll have A, we'll have B, and we'll get the result returned in another register of A plus B. However, our registers are a lot wider than just this single float value. In fact, if we're using the AVX2 mode, we can, by invoking one add operation, in fact add multiple floats together at the same time, and we can do multiply and subtract and various other mathematical and logical operations are in there. So basically we can start invoking more things together. Now this does have quite a few advantages, and in particular in these simple simulations I'm doing, we can do a lot of work. Now I went down quite a deep rabbit hole when I was doing this, so there is the ability to get some auto vectorization if we lay our code out in a particular way, and it is very useful that a lot of the time if we start doing things, we can get some auto vectorization. The downside is this is not always automatic, so it makes sense for us to try and lay out our code in a particular way and then use these SIMD instructions to do things. So it's generally better for us to write our own code, and as I say, it's a different mindset which normally involves us writing in structure of array format rather than array of structure format, because intrinsics work well with this. I suppose a couple of things as well that we need to think about. The biggest thing is we need to load and store data to and from the registers. So unlike when we use normal variables, we can just directly assign them. In most cases, what we're going to do is we're going to have an array of floating point values. We want to load that array of floating point values into a register or store it into register type, and then we do operations on it. To access that data later, we must get that data back out by storing it back into an array. So these load store operations are something we should try and avoid in any critical path, because these are slow, because we're going to and from these registers, we're packing and unpacking data. So they're inevitable that we're going to use them, but this is where our slow path will appear in our code. And in particular, we'll do something along this line. So in this case, what we've got here is just a 4 float register, so an M128. Here's our data, and what we're doing is we're loading that data directly into a value, and that gets returned into the register. And on some compilers, we can access that using a subscript operator on the register. That is not how we should do it, and so on. Now, what I'm going to do is I'm going to jump off now and have a look at a code design that I've done for doing this sort of thing. And basically I decided what I was going to do to start with, and as we'll see later, this was actually not the best approach to take, and it did cause a few issues, is I'm going to create a vec3 by 8 class. So what this represents is a vec3 data type, but instead of it being a single vec3, every time I create one of these, it's going to actually be 8 vec3s together. And in this case, I can construct it, default construction. I can construct it from an array of NGL vec3s of 8 NGL vec3s. I can copy it, so copy constructor. I can construct it by using the _M256 intrinsic. So this is our data type for the YMM registers, the 8 floating point value registers in there. We can also set it from a single vec value, which will basically set all of the lanes to be the correct thing and so on. And you can see I've written some overloaded operators here to do certain things and access the data. And basically what we've got here now is an array of 8 x's, an array of 8 y's, and an array of 8 z's. So if we call some of these overloaded operators, what's going to happen is, so my default constructor assigns all of the 8 floats to 0, 0, 0. The single floating value, so if we passed in 1, it would set them all to 1, so all the lanes to 1. In the copy, this is just passing in the x, y, and z of the vec3, so again it's setting those to 1 values. And passing in the registers, it's copying them through and so on. If I pass in an array of 8 vec3s, what I have to do is loop through, store all of the x's, store all of the y's, store all of the z's, and then load that into the register. In this case, I've got an operator to subscript, and all this is going to do is return an NGL vec3, which is either 0, 1 through 3, 4 through to 8. So we just go through. So in this case, what I've got to do is copy the value from each of the registers into an array of 8, and then return the one based on the subscript. Note no error checking or anything in there, so it's not particularly safe. Now this is where things really come into play, because if I wanted to multiply 2 vec3 by 8s, then all I have to do is to multiply the x's, the y's, the z's. This is going to multiply 8 floats each way through, and then return a new one, which is the product of those two. By a scalar, similar sort of thing. Notice I'm creating a scalar which is 8 individual floats through. Other way around, it's a clamp operation, so I'm clamping min and max. I'm only writing the code that I need in this, so I've got my plus operator. I haven't done a minus operator because I'm not using it in my code. I'm using the sort of you ain't going to need it principle of code here. And I've got dot products here, multiply operator to multiply the registers together. I've implemented the reflect function that's there, and I've implemented the plus equals operator as well, so I'm adding one to the other. And there's a series of unit tests there as well, because it's always good to do some unit tests to test all of these things, and it works, but there is a flaw to this design, as we'll see when we look at the code. I did this because my code is initially using NGL vec3s. What I'm going to do now is do 8 vec3s at a time and go through my code. And it does work, and we will see a speed up, but what we'll see is the code is not particularly nice, which we'll look at in the next demo.